Swayam Prabha. Digital India. Educated India.
Welcome. In the last class, we have been discussing the velocity correlation function for the purpose of deriving what we said as Einstein relation for diffusivity. And so far, we have found the velocity correlation function again for Brownian motion of a free particle as the following. So, Vt prime ensemble averaged is equal to kBt by m exponential of minus t prime absolute value by tau v, and this function is even, that is, it is same for negative times and positive times, and so it satisfies the relation we have earlier established for the autocorrelation functions. Okay. So, now if I want to take it further, ultimately I said that I will relate the displacement correlation function with this velocity correlation function, because from displacement correlation function we can get the mean square displacement, and then we can get the relation for the diffusivity, and that is what we will do it now. So, we have earlier derived in the class, in the lecture, that if I want to find the mean square displacement, this has to be twice of this, and this particular thing for T2 higher than 0. So, anyway we integrate T2 from 0 to T1. So, it is always higher than 0. So, this is e to the power minus T2 by tau v multiplied by kBt by m. So, this becomes 2 kBt by m 0 to t dt1, and if I integrate the exponential, what I do get now. There is a small detail here, or the assumption that we make, and the assumption is like, if I look at the tau v is my m by zeta. This is some sort of a time scale that characterizes the diffusion. If that time scale is very small compared, actually tau v is a time scale that characterizes the time scale of dissipation, to be more specific, because we are dividing the mass by the friction coefficient that we had. So, if this time scale is very small compared to the time scale we are interested in or the time scale of diffusion, that is to say if T2 is much higher than tau v, which is not so much of a bad assumption because tau v is typically of the order of say 10 nanoseconds or smaller, and we may be interested in the times maybe like in microseconds or milliseconds or seconds. Those times will be very high compared to the tau v. So, in that case we make use of the fact that ultimately the integrand here is an exponential function that would decay with time, and so of course at T2 equal to 0 it is equal to 1, but at T2 equal to T1 it is already a very small number. So, even if I change the upper limit to say infinity, that would not really change the result by a lot, but it would simplify our analysis quite a bit, right. And that is only true when this T2 and T1 to be more specific in this case is much higher than TV. Actually, if the idea of like dummy variables confuse us, all we need to care about is what is the time scale that we want to study for the diffusion problem and what is the time scale we get from m by zeta. And as long as the time scale we want to study for diffusion problem is much higher than that tau v, then in that case we can make this particular approximation that I can change the upper limit from T1 to infinity, because in any case that would make very small numerical error and it would be a great simplification in what we will do next. Okay. So, that is what I will do here. So, now the upper limit goes to 0 and we only have the lower limit. So, that is then it is equal to 2 kBt by m, and tau v comes outside. So, we have an m by zeta coming here. Only the lower limit will remain there, and the lower limit anyway is equal to 1 because we have taken the prefactor out. So, this is equal to 2 kBt by zeta multiplied by t. So, what we therefore get is my mean square displacement is equal to this, and if I associate this quantity that we get as my diffusion coefficient, then this is equal to twice of 2 dt, and this makes perfect sense because now d is a ratio of the mean square displacement with the time, and that is what we have begun from, because we said that the d has a unit of meter square per second. It characterizes the mean square displacement the particle undergoes and so on. There are 2 points to be made here. The first point is, of course, we have done it in only one dimension. If I am doing in say a general 2 dimension or a 3 dimension, in this case only change we will see in the d dimension is we will have the factor d there. So, for example, in 3D this is equal to 6 dt, in 2D this is equal to 4 dt and so on. That is the first point. The second point is, let us say I want to compare this behavior with, say, the mean square displacement if for a normal rectilinear motion when things are moving in a particular direction without experiencing collision. So, in that case we know that the distance travelled should be proportional to the time, and x should be equal to something like Vt plus some initial value for a rectilinear motion. So, in that case what we do get is x minus x0 square would simply be proportional to t square. So, if we think of a motion that is like a rectilinear motion or motion of a projectile, for example, in that case we see that my mean square displacement goes like t square. In the case when we are thinking of a diffusive motion, where motion is because of the collisions we get from surrounding molecules, then the mean square displacement goes like t, that is basically square root of the result that we had for the case of rectilinear motion. This is what is called a diffusive motion. So, if the mean square displacement is proportional to t, that is what I will call a diffusive motion. If we have some deviation from this particular power law, we will call it a non-diffusive kind of motion or non-Fickian kind of diffusion and so on, right. So, the whole notion that the mean square displacement should go like t was given by Einstein, and it still serves as the basis of how we understand diffusion. So, now I want to take discussion a bit further. So far we have been talking about Brownian motion of a free particle. Of course, a polymer is first of all a large molecule, and we typically represent a polymer by, say, segments connected together by some sort of bonds, and therefore, if I want to represent the Brownian motion of a polymer chain, it is probably better that we talk about Brownian motion of the individual segments of the polymer chain. That is to say that if I now look at a polymer chain, and we can think of any model, but let us say we think about a bead spring model, then we have beads connected by springs, and all these beads are then surrounded by water molecules, and they are all undergoing some sort of Brownian motion, right. So, of course, we could have said that I would represent the polymer motion by simply assuming that this entire polymer chain is some sort of an effective shape object and think of the Brownian motion as the motion of this object as a result of solvent collisions. Okay. So, I will do the model right here is not bad because still it captures the effect of like solvent collisions. It does not capture the internal motion of polymer segments. The polymer segments will also have some internal motion. That is the whole reason why polymer can take multiple conformations, and those conformations can also be because of the Brownian motion of the individual segments. That behavior is not captured if I treat the polymer chain as a single entity. So, it is we are better off if we treat a polymer chain as composed of these beads. This is not really a problem if I think of, for example, say a metal ball, So, in that case the internal motion of metal atoms is not important. You will see a net motion of metal ball, although metal ball really has to be very small for Brownian motion to be of any significance, but the internal motion of the atoms inside the ball will not be of much significance. But in this case of polymer chains, since the segments can rearrange themselves and we can have various conformations, those conformations also result from this kind of Brownian motion, and therefore we should think of Brownian motion in the case of a polymer chain in terms of the motion of these individual segments or beads. That is the first point. So, we will go with this picture, not with this picture. The second point is, if I now look at this polymer chain in motion because of say the Brownian motion, the solvent collisions are not the only force acting on every bead. Now, what you will have is every bead, let us say if I look at this particular bead here, then this bead is interacting with the two neighboring beads by the two springs that connects them, right. So, if I move this bead by little bit, even these two guys will get affected, and that is how we include, that is why we include some sort of a spring. So, if I let us say pull one guy, other guys will also experience some force and respond to that kind of emotion. Okay. So, we also have to have some way to incorporate that spring force in addition to the force due to thermal motions. That is not the drag force. The drag force is because of solvent molecules in the system. The thermal motions are also because of solvent molecules in the system. One is dissipative in nature and other has a fluctuation type of nature. But this force, that is spring force, is internal to the system. It is between the two beads in the polymer chain or two segments in the polymer chain, and this is some sort of an external force acting on each of these beads. Okay. So, therefore, the way we will develop the model of a polymer chain, if we first discuss how the Brownian motion changes in the presence of an external field, because every bead is experiencing an external field, that is my spring force, and then we will, using that equation, we will then describe the Brownian motion for a bead spring model of a polymer chain. So, let us first talk about the Brownian motion in an external field, and let us say for the time being take the same problem that we started with, a free particle that is undergoing a Brownian motion. The only thing is that now there is also an external field acting on it. So, we still have a free particle, but now we also think that the external field is acting on the system, and then we can generalize that for the case of a polymer chain. This can be, for example, be a scenario where we have an electric field being applied on the system. Now, of course, that system will not be in equilibrium, but nowhere in the description of the Brownian motion, the equation of motion, we have assumed the equilibrium nature. The equilibrium nature comes much later when we talk about, for example, the correlation functions and so on. The Brownian motion equation, the equation of motion itself is applicable also in that scenario. But then when we do the case of a polymer chains, then those, as I have just said, the spring forces are not really external to the system, they are internal to the system, and therefore the polymer chain can very much be in equilibrium, although it is experiencing some spring forces between the segments. Those forces still are present, but they are not external to the system. It only sets the ground This model only sets the ground for the description of polymer models that we will do. So, in this case we still have, so let us say if I look in one dimension, so we still have the two terms that we had discussed. In addition to that, we now also have a force term that is simply a gradient of the external field, and I am doing in one dimension. That is, the motion is only happening in one dimension. Okay, you can do in any dimension, but the math will simply look somewhat complicated, but simply you will replace the dou u by dou x by del of u, but the idea remains quite the same. So, in this case again, if the tau v is much smaller than the time scale under consideration, here the tau v is my m by zeta. So, if m by zeta is very small, what it means is my inertial term is very small compared to my drag term, because m is small and zeta is higher, would give me a smaller value for m by zeta. So, in this case I can drop m x, that is my inertial term. That is not a bad approximation in many cases, as long as either the mass is very small or the friction is high enough. In that case we can drop the inertial term, and we have so this gives me so this particular quantity f r by zeta will have units of velocity, because we have a velocity here. So, I would call it as the random velocity that we impose, because anyway zeta is a constant here, and then I have a term coming from the external field that is present in the system. So, now this VRT satisfies similar relations as FRT does. So, VRT is equal to the ensemble average is equal to 0, and if I look at the auto correlation, that has to be delta of t minus t prime, and A was 2 zeta kBt in the case of FRT prime. In this case I am dividing by zeta, so it is 2 zeta kBt divided by zeta square. So, zetas will cancel, so it is 2 kBt by zeta, and kBt by zeta is my diffusion coefficient. So, we have 2d delta t minus t prime. So, this becomes the equation of Brownian motion in the presence of an external field u. Okay. So, let us take an example. Let us say that this u follows some functional form. For example, if u is half kx square, you can see where we are going, because ultimately these are the kinds of forces which apply in a polymer chain, but now we are applying them on a single solute particle in solution. So, in this case minus dou u by dou x is equal to minus k x, and therefore, we get dx by dt is equal to k by zeta x plus VR t. Again the VR satisfies the relation that we have derived. So, we will start from this particular point, the Brownian motion of a free particle in external field that we have derived today, and we will use it to discuss the Brownian motion of a bead spring model of a polymer chain in a solution by a simple extension of what we have done in this particular lecture. Thank you.